Okay, number 10, I'm going to break into two parts here, part A and part B. Given the percent composition and experimental molar mass, be able to determine both empirical and molecular formulas. So in part A here, we're going to talk about the empirical formula. It's the simplest ratio. So again, there's a format or an algorithm we can follow here. Since the formula is all about how many moles or atoms are in there, we need to change our grams, our percent composition, into moles. So when I see a compound contains 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen, I can really think of each of those amounts as grams because out of a 100-gram sample, I know the percents in grams would be interchangeable. So my first step is change my grams to moles for each. So I've got carbon at 48.64 grams, and I know 1 mole of carbon weighs 12.01 grams. So that means we're really talking about around 4 moles here. 48.64 divided by 12.01. This is 4.050 moles of carbon. My hydrogen, 8.16 grams. When a mole weighs 1.01, means I've got a little over 8 here, 8.079 moles of hydrogen. And then finally my oxygen at 43.20. 1 mole weighs 16 grams. So 43.2 divided by 16 is 2.700 moles of oxygen. So now I write my formula with my very strange subscripts. C 4.050, H 8.079, and O 2.700, and I divide by the smallest amount and see if that gives me whole number ratios or not. Well, for C, that changes 4.05 divided by 2.7. This becomes 1.5. My H becomes 2.99 or 3, and my O is going to be 1. And what this means is my ratio is 1.5 to 3 to 1, or in whole number speak, I would double that to take the whole thing times 2. It's really C3H6O2. And that's my empirical formula for this particular substance.